Introduction to partitions in Linux. In this video, we are going to see about introduction to partitions in Linux. It may seem strange that Linux uses more than one partition on the same disk, even when using the standard installation procedure, so some explanation is called for. One of the goals of having different partitions is to achieve higher data security in case of disaster. By dividing the hard disk in partitions, data can be grouped and separated. When an accident occurs, only the data in the partition that got the hit will be damaged, while the data on the other partitions will most likely survive. The use of partitions remains for security and robustness reasons, so a breach on one part of the system doesn't automatically mean that the whole computer is in danger. This is currently the most important reason for partitioning. There are three types of partitions. They are primary partition, extended partition, logical partition. Primary partition. It is a file system container. At least one primary partition must exist during the partition. It can be extended up to 4 on a single physical disk. It will be identified with number 1 to 4, such as /dev/hda1, /dev/hda2, and so on. Extended partition. It is a variant of a primary partition, but it cannot contain a file system. Instead, it contains one or more logical partitions. Only one extended partition may exist, and it takes one of the 4 possible spots of primary partitions. Logical partition. Logical partition created within the extended partition. From 1 to 12, logical partitions may be created. They are numbered from 5 to 16, such as /dev/hda5, /dev/hda6, and so on. File systems. A file system is the methods and data structures that an operating system uses to keep track of files on a disk or partition. That is, the way the files are organized on the disk. The word is also used to refer to a partition or disk that is used to store the files or the type of the file system. A few programs operate directly on the raw sectors of a disk or partition. If there is an existing file system, there it will be destroyed or seriously corrupted. Linux native file systems. One of the most important features of Linux is its support for many different file systems. This makes it very flexible and well able to coexist with many other operating systems. At the time of writing, Linux supports 15 file systems: ext, ext2, xia, minix, ums-dos, ms-dos, vfat, proc, smb, ncp, ISO 9660, SYSV, HPFS, AFFS, UFS. And no doubt, over time, more will be added. Linux adds each new file system into this single file system tree as it is mounted. All file systems of whatever type are mounted onto a directory, and the files of the mounted file system cover up the existing contents of that directory. This directory is known as the mount directory or mount point. When the file system is unmounted, the mount directory's own files are once again revealed. Introduction to Inodes. In this video, we are going to see about Introduction to Inodes. Inodes contain file and directory metadata and provide a mechanism for linking data stored in data blocks. When a file or directory is created on a Linux file system, an inode is assigned that contains the following information: the mode and type of the file or directory, the number of links to a file or directory, the UID and GID of the files or directory's owner, the number of bytes in the file or directory, the files or directory's last access time and last modified time, the inode's last file status change time, the block address for the file data. Inodes contain modification, access, and creation, that is MAC times, not file names. An assigned inode has 13 pointers that link to data blocks and other pointers where files are stored. Pointers 1 through 10 link directly to data storage blocks in the disk data block and contain block addresses indicating where data is stored on the disk. These pointers are direct pointers because each one is associated with one block of data storage. Directories in Linux. In this video, we are going to see about directories in Linux. Every operating system organizes information into files. These files are stored in different directories. A set of such directories may be contained in one directory known as the parent directory, and the directories contained in it are known as subdirectories. There is a main directory in every operating system that contains all directories and files of the system. Such a hierarchical organization of information on a system is known as a file system. In every file system, there is a main directory that contains all the data of the system in forms of directories and files, where each directory may contain a number of subdirectories and files. The Linux file system is also organized in such a hierarchical structure. The main file in a Linux system is known as root. The root directory is represented by a slash. When we open a file, we always start from the root directory and move to the subdirectories of sub-subdirectories containing the file. Data of the file system may be present on a hard disk, floppy disk and a CD-ROM. For example, data, data, and data are three different files that may be contained in the same directory. Inodes. In this video, we are going to see about inodes. Index node is equal to inodes. With each file and directory in a file system is associated an inode, which has all detailed information about the file except its name and contents. The name and inode number of a file are found in the directory that is its parent. It is a method of knowing how files are stored on a disk. Associated with each file is a table called an inode, that is index node. It has an internal representation of a file, that is attributes of a file such as owner and access permissions. Inode of a file is present on the disk in a static form, and when the file is opened and loaded into the memory, its corresponding inode is loaded or copied into an in-core inode table. File owner identification, user, group. File type, regular, character special, directory, block special. File access permissions, file access times, file modification time, file creation time, number of links to the file. Table of contents for disk addresses of data in a file. Although the users treat the data in a file as a logic stream of bytes, the kernel saves the data in discontinuous disk blocks. The inode identifies the disk blocks that are associated with a particular file. File size. Data in a file is addressable by the number of bytes from the beginning of a file, starting from byte offset 0 and the file size. The inode number is basically the position of the inode in the inode array and thus need not be stored. It can be obtained through simple calculation. Structure of a directory. In this video, we are going to see about structure of directory. Though directories are also considered as file in Unix, these have different internal contents as compared to regular files. The contents of regular files can be programs, shell scripts, etc., whereas the contents of a directory are other directories and files. Writing into a directory by a user means that he or she can create or remove files from this directory using Unix commands, but no user is actually followed to write the contents of a directory. The kernel does this job automatically when a user is actually allowed to write the contents of a directory. The kernel does this job automatically when a user creates or removes files. The directories provide the file system its hierarchical structure and play a very crucial role in converting a file name or path name to an inode number. A directory contains a sequence of entries consisting of a 14-character long file name, 2 bytes long inode number, and the byte offset in the directory. In each directory are housed 2 files and signifying the parent and the current directory respectively. That is, they have the inodes of current and parent directory. This provides the hierarchical structure. An inode entry of 0 signifies that this byte offset of directory is free to house a new inode. For example, directory entry at byte offset 128 is empty, though it once housed a file called 0 file. The program mkfs initializes a file system so that and of the root directory have the root inode number of the file system. The kernel stores data for a directory just as it stores data for a regular file using the same structure of 10 direct, 1 each single, double, triple indirect blocks. The kernel reserves the right to write to a directory to ensure its correct structure. CP and inodes. In this video, we are going to see about CP and inodes. The simplest version of the copy command is cp file1 file2. Issuing this command copies the contents of file 1 and places them in file 2. The destination file will have a new creation data and inode number. Other copy command to copy the contents of one more subdirectories. The below table explains how cp command works. An inode is the identifier used on each Linux partition for a file. Every file gets its own inode. The inode includes metadata about the file, which includes the permissions, size, last time access time, and the disk block where the file is located. If the inode is misaligned or corrupted, Linux won't be able to find the associated file. The cp file1 file2 command doesn't work if you are copying a file from one partition to another. MV and inodes. In this video, we are going to see about MV and inodes. If you want to rename a file in Linux, you move it. The MV command changes the name of a file. Unless you are moving a file to a different volume, everything about the file, including the inode number, stays the same. There are 4 key move commands. They are shown in below table. Moving multiple files with one MV command. One advantage of the Linux MV command is that you can specify multiple source file names on the command line and have they all copied to the same destination directory. RM and inodes. In this video, we are going to see about RM and inodes. You can use RM to remove files and directories. This is one of the reasons many Linux administrators are advised to run Linux in root or superuser mode only when necessary. Small mistake in this command can easily delete all of your Linux files. For example, suppose you want to remove a group of temporary directories in your root /directory a.temp, b.temp and c.temp. You want to use the rm r*temp command, but instead you type the following #rm r*temp. Because there's a space between the asterisk and .temp, the shell assumes you want to recursively delete all directories and then delete the file named .temp. The result is not good. For this reason, Red Hat configures the following as an alias for the root code: alias rm *rm I. The alias ensure that whenever you use the rm command, that is even rm r, the shell prompts you for confirmation before you delete any files. Some Linux distributions set up this alias as a shell variable for root users. The key rm commands are shown in the below table. Hard links. In this video, we are going to see about hard links. A hard link to a file appears as another file in the structure. If the link appears in the same directory as the linked to file, the links must have different file names because two files in the same directory cannot have the same link. Link creates a hard link. The ln, that is link utility, that is without the s or symbolic option, creates an additional hard link to an existing file using the following syntax: in existing file, new link. The next command makes the link shown in the below figure by creating a new link named /home/alex/letter to an existing file named draft in Jenny's home directory. The new link appears in the /home/alex directory with the file name letter. In practice, Alex may need to change directory and file permission. The link utility creates an additional pointer to an existing file but does not make another copy of the file. Because there is only one file, the file status information such as access permission, owner and the time the file was last modified is the same for all links. Only the file names differ. When Jenny modifies /home/Jenny/draft, Alex sees the changes in /home/Alex/letter. Symbolic or soft links. In this video, we are going to see about symbolic or soft links. In addition to hard links, Linux supports links called symbolic links, soft links or symlinks. A hard link is a pointer to a file, that is, the directory entry points to the inode, whereas a symbolic link is an indirect pointer to a file, that is, the directory entry contains the path name of the pointed to file, a pointer to the hard link to the file. symbolic links were developed because of the limitations inherent in hard links. You cannot create a hard link to a directory, but you can create a symbolic link to a directory. A symbolic link can point to any file regardless of where it is located in the file structure, but a hard link to a file must be in the same file system as the other hard link, that is S to the file. Often, the Linux file hierarchy is composed of several file systems. Because each file system keeps separate control information, that is, separate inode tables for the files it contains, it is not possible to create hard links between files in different file systems. When you create links only among files in your own directories, you will not notice these limitations. One of the big advantages of a symbolic link is that it can point to a non-existent file. This ability is useful if you need a link to a file that is periodically removed and recreated. A hard link keeps pointing to a removed file, which the hard link keeps alive even after a new file is created. A symbolic link always points to the newly created file and does not interfere with deleting the old file. For example, a symbolic link could point to a file that gets checked in and are under a source code control system A.0 file that is recreated by the C compiler each time you run make, or a log file that is periodically archived. Although they are more general than hard links, symbolic links have some disadvantages. When a file has multiple hard links, it is analogous to a person having multiple full legal names. In contrast, symbolic links are analogous to nicknames. Anyone can have one or more nicknames, but these nicknames have a lesser status than legal names. Link creates a symbolic link. Use in with the symbolic or S option to create a symbolic link. The following example creates a symbolic link /temp/s3 to the file sum in Alex home directory. When you use the ls-l command to look at the symbolic link, ls displays the name of the link and the name of the file it points to. The first character of the listing is L for link. The 7 fundamental file types. In this video, we are going to see about the 7 fundamental file types. There are 7 file types in Linux. Everything that goes in the file tree must be one of the types given below. The type indicators show up at the very front of the file listings. You can specify which file types to look at with the find command. Ctrl-C interrupts find if it goes on for too long. File types definitions. Let's take a closer look at what the file types in Linux really are. Regular files. plain OLE text and data files or binary executables, directories, list of files, character and block devices, files that could be considered as meeting points between the kernel and device drivers. For example, /dev/hda, that is IDE hard drive, /dev/ttys1, that is serial modem, and so forth. These allow the kernel to correctly route a request for various hardware devices on your system. Local domain sockets. Communications between local processes. They are visible as files but cannot be read from or written to except by the processes directly involved. Named pipes. Also for local inter-process communications. It is highly unlikely that a Linux user will ever need to do anything with either sockets or pipes. They are strictly system functions. Links. Links are of great interest to Linux users. There are two types: hard links and soft links. Links are pointers to files. A hard link is really just another name for a file as it points to a specific inode. All the hard links that point to a file retain all of the file's attributes, permissions, ownership, and so on. RM will happily delete a hard link, but the file remains on disk until all hard links are gone and all processes have released it. Soft links point to a file name. They can point to any file anywhere. You can even create dead soft links by deleting the files they point to or changing the names of the files. Checking free space using df command. In this video, we are going to see about checking free space using df command. You can quickly and easily check free space on your system using the df command. The output of the df command contains a lot of information. Information is displayed on a separate link for each file system you have mounted. In this example, two file systems are mounted. /dev/hda1 mounted at / and /dev/hda3 mounted at /home. For each entry, the size of the file system in 1 KB block is displayed in the 1 KB blocks column. For example, the size of /dev/hda1 is 6,14,649 KB or 600 MB. For each entry, the amount of disk space in use is displayed in kilobytes in the used column. For each entry, the amount of disk space available is displayed in kilobytes in the available column. For each entry, the percentage of disk space in use is displayed in the use percentage column. For each entry, the location where the file system is mounted is indicated in the mounted on column. In the example, /dev/hda1 is mounted at / and /dev/hda3 is mounted at /home. Using the df command, You can also display the free space on a particular partition. For example, to see how much disk space is free on /dev/hda1, pass the partition co the command as an argument. You can also determine the amount of free space on a file system by specifying a path on the command line. The df command displays the amount of disk space available on the file system where the specified path or file name exists. In this example, the path /user/local is also on the /dev/hda1 file system. Removable media. In this video, we are going to see about removable media. In general, removable media should not be mounted automatically during the boot process. That's possible in the /etc/fstab configuration file with an option like no auto, but in general it's not standard in RHEL to set up removable media in /etc/fstab. To read removable media such as smart cards and CD/DVDs, RHEL somewhat automates the mounting of such media in the GNOME or KOE desktop environments. While the details of this process are not part of the Red Hat exam PREP guide, the process is based on configuration files in the /etc/udev/rules.d directory. If RHEL detects your hardware, click Places in the menu that appears. Select the entry for the removable media. If multiple removable media options are loaded, you can select the media to mount in the removable media submenu. If that doesn't work for some reason, you can use the mount command directly. For example, the following command mounts a CD/DVD in a drive. The T-switch specifies the type of file systems, that is ISO 9660. The device file /dev/sro represents the first CD/DVD drive. /mnt is the directory through which you can access the files from the CD or DVD after mounting. Linux addresses that in a couple of ways. First, it sets up links from more sensibly named files such as /dev/cd-rom, which you can confirm with the ls f/dev/cd-rom command. Second, try the blkid command. If removable media, that is other than a CD or DVD, are connected, you will see it in the output to the command, including the associated device file. Just remember that it is important to unmount removable media such as USB keys before removing them. Otherwise, the data that you thought was written to the disk might still be in the unwritten RAM cache. In that case, you would lose that data. Given these examples of how removable media can be mounted, you should have a better idea on how such media can be configured in the /etc/fstab configuration file. The standard defaults option is inappropriate in most cases as it mounts a system in read-write mode, that is even for read-only DVDs. Attempts to mount automatically during the boot process and limits access to the root administrative user. But that can be changed with the right options. For example, to configure a CD drive that can be mounted by regular users, you could add the following line to /etc/fstab. This line sets up a mount in read-only mode, does not try to mount it automatically during the boot process, and support access by regular users. As desired, similar options are possible for removable media such as USB keys. But that can be more problematic with multiple USB keys. One may be detected as /dev/sdc once and then later detected as /dev/sdd if there's a second USB key installed. However, if properly configured, each USB key should have unique UUIDs. As described earlier, UUIDs are the RHEL6 way to identify different volumes to be mounted in /etc/fstab. Mounting CDs and DVDs. In this video, we are going to see about mounting CDs and DVDs. On most Linux platforms, there's a daemon running in the background that will automatically mount the CD or DVD. For systems that do not have such a daemon, you must mount the CD or DVD manually. You may need root privileges in order to give the mount command. The following are typical mount commands for various systems. The name of the device representing the CD or DVD is different on different systems. To determine the device names, consult the documentation for your platform. In the following commands, the CD or DVD mount point that is represented by /media could be different for your platform. Common CD mount points are /CD-ROM and /MNT/CD-ROM, and common DVD mount points are /DVD-ROM and /MNT/DVD-ROM. Mount RT/UDF/device/media or mount R/DEV/device/media. If the file names on the CD or DVD appear in the wrong case, it means the CD or DVD is mounted incorrectly. On some Linux systems, the CD or DVD may be mounted automatically with the No EXEC option. This prevents binaries on the disk from being executed and may cause permission denied messages to appear during installation. The solution for this issue is to unmount the CD or DVD using unmount/media and then manually remount the disk using the appropriate command shown in the table. After you have finished using the CD or DVD, you must unmount it. Typically, the unmount command ISU mount/media before unmounting the CD or DVD makes sure that no programs are running from the CD or DVD. No files are open and no users have a directory on the CD or DVD as their current working directory. Mounting USB media. In this video, we are going to see about mounting USB media. Because of their large capacity and portability, removable storage devices are commonly used today to store backups of data, pictures, music, movies, programs, and documents. These devices, which typically connect to your PC via high-speed USB or FireWire cables, include flash memory drives, external hard drives, digital camera, media players, smartphones, tablets. Nearly all removable storage device manufacturers emulate the SCSI protocol in the firmware of the device itself. If a GUI environment is loaded, Fedora 20 recognizes removable media devices that connect to your PC via USB or FireWire cables as SCSI devices and automatically mounts them to a new directory under the /run/media/username directory named for the label on the device, much like CD and DVDs. Additionally, you will be able to access or safely eject your device using the associated icon in the Files application within the GUI environment. Since it is common to work with removable media devices within a GUI environment, understanding the device names and mount point directories used by the devices themselves is often irrelevant. You can work with the files on removable media devices by accessing the appropriate icons in the Files application that represent the devices in the GUI environment. However, if you are working in a command line terminal, you need to keep track of when a USB or FireWire storage device is plugged into the computer in order to understand which device file the Linux operating system will assign to it. For example, if your Linux system has two hard disks, that is /dev/sda and /dev/sdb and PATA DVD drive, the next available device file for a newly inserted USB flash drive would be /dev/sdc, and the first partition on that device would be referred to as /dev/sdc1. As a result, you could create a mount point to the directory for the USB flash drive under the /media directory and mount the device to this directory as shown here. The mount command. In this video, we are going to see about the mount command. Mounting a disk is done with the mount command. In its most common form, using mount is a simple and straightforward procedure. All that's involved is picking a location somewhere in the directory tree to attach your disk, making sure that an empty directory is located there, and issuing the appropriate mount commands. FreeBSD ships with an empty or MNT directory, which is intended for use with disk that you mount temporarily or only once in a while. We will use that directory for some of our examples. However, you can mount any volume anywhere you like. For example, you can create a floppy mount point on which to mount floppy disk. Just make sure to create the mount point directory first, #mkdir/floppy. Mounting a volume requires you to specify the device name of the disk, that is, provided the disk is in the drive, in the case of removable disk, and the mount point like so: #mount/dev/fdo/mnt. Done correctly and assuming that no errors occur. There should be no output. You should be able to use the new file system immediately. Use the df commands to see if it worked. The last line shows the /dev/fdo device, the floppy disk mounted at /mnt. You can now use ls/floppy to see the disk contents and copy files back and forth to and from the disk's file system. Archiving and compressing files. In this video, we are going to see about archiving and compressing files. Now that you have learned about files, permissions, and possible errors, you need to master gzip and tar. Gzip. The program gzip, that is GNU zip, is one of the current standard Unix compression programs. A file that ends with .gs is a GNU zip archive. Use gunzip file.gz to uncompress file.gz and remove the suffix. To compress it again, use gzip file. Tar. Unlike the zip programs for other operating systems, gzip does not create archives of files. That is, it doesn't pack multiple files and directories into one file. To create an archive, use tar instead. $tar cvf archive.tar file1 file2. Archives created by tar usually have a.tar suffix, that is, this is by convention, it isn't required. For example, in the command above, file1, file2, and so on are the names of the files and directories that you wish to archive in archive.tar. The C flag activates create mode. The R and F flags have more specific roles. The V flag activates verbose diagnostic output, causing tar to print the names of the files and directories in the archive when it encounters them. Adding another V causes tar to print details such as file size and permissions. If you don't want tar to tell you what it's doing, omit the V flag. The F flag denotes the file option. Compressed archives, that is .tar.gz. Many beginners find it confusing that archives are normally found compressed, with file names ending in .tar.gz. To unpack a compressed archive, work from the right side to the left. Get rid of .gz first and then worry about the .tar. For example, these two commands decompress and unpack file .tar.gz. $gunzip file.tar.gz. $tar xvf file.tar. When starting out, you can do this one step at a time. First, running gunzip to decompress and then tar to verify and unpack. To create a compressed archive, do the reverse. Run tar first and gzip second. Zcat. The method shown above is in the fastest or most efficient way to invoke tar on a compressed archive. and it wastes disk space and kernel input or output time. A better way is to combine archival and compression functions with a pipeline. For example, this command pipeline unpacks file.tar.gz. The zcat command is the same as gunzip dc. The D option decompresses and the C option sends the result to standard output, that is, in this case, to the tar command. Because it's so common to use zcat, the version of tar that comes with Linux has a shortcut. Creating, listing and extracting tar file archives. In this video, we are going to see about creating, listing and extracting tar file archives. Creating compressed tar files. The tar program included with most Linux distributions has integrated support for gzip compression. This means you can compress the tar archive files you create at the time of creation rather than first creating the file and then compressing it. To do this, you need to extend the method used for creating tar archive files, as discussed in the tip, creating a tar file archive by adding the Z option. This option indicates to tar that you want to create a compressed tar archive files rather than a standard uncompressed tar archive file. Your tar command should look like this: $tar CSVF compressed tar file name, files or directories, enter. Compressed tar archive files typically have .tar.gz extensions. At times, you will encounter compressed tar archives with .tgz extensions. Listing the contents of tar archives. You can use the Linux tar command to display a list of the files contained in a tar archive or a compressed tar archive. To view a list of files in an existing tar archive, you use the following syntax with the tar command: $tar options, tar file name, enter. The options for extracting a tar archive are: put together. These three options tell the tar program that you want to display a detailed list of files in an archive file. For example, to display a complete list of files in a tar archive, name test.tar stored in the /temp directory, use the command $tar cvf/temp/test.tar, enter. To view a list of files in a compressed tar archive file, add the Z option to tell tar you want to view the contents of a compressed archive file. $tar tsvf/temp/test.tar.gz, enter. Extracting files from compressed tar files archives. The tar program included with most Linux distributions has integrated support for gzip compression. This means you can extract compressed tar archive files in one step instead of uncompressing a file and then extracting files from it. To do this, you need to extend the method used for creating tar archive files as discussed in the tip, extracting the file from tar file archives by adding the Z option. This option indicates to tar that you want to extract from a compressed tar archive file rather than a standard uncompressed tar archive file. Your tar command should look like this: $tar xsvf compressed tar file name, enter. Compressed tar archive files typically have .tar.gz extensions. At times, you will encounter compressed tar archives with TGZ extensions. Creating file archives, other tools. In this video, we are going to see about creating file archives, other tools. Control files. Linux is based around files. By modifying files, you can control almost everything. Rather than editing files on different servers in the way that you require, you can specify this on the Puppet master. The Puppet agents will ensure that the same file is present on the server where it is installed. For example, you have a custom /etc/ssh/sshd config and /etc/sudoers file that locks down SSH and gives root access to admins. You can roll out these files automatically and any future changes with Puppet. If someone, such as an attacker, changes or overwrites any of the Puppet-controlled files, the desired changes will be put back. Set cron jobs. Puppet can set cron jobs on a server from the Puppet master on all of your servers, so you can schedule jobs anywhere without having to manually set these up. Install or remove packages. You can ensure that packages are installed or removed from your servers. For instance, if you need Apache, you can ensure that it's always there along with the required configuration files that you have set. Alternatively, if you want to ensure that Apache is removed, you can set this as well. If someone installs Apache, then Puppet will remove it. Ensure services are running. Puppet can check to ensure that services are running or stopped. For example, you can ensure that Apache is always up and running. If Puppet detects that Apache is not running, it can try to start the service. Execute commands. You can also set Puppet to run a command on all of your servers. So, you could use Puppet to run the auto install command for the antivirus agent to have it installed automatically on all of your servers that you wish to monitor, saving a lot of time.